We're up to 50. So Masood, I take it you fixed the beeping when people enter. That was good.
Yes.
How do you adjust that? I was trying to figure that out.
I required to go to the Zoom account.
Oh, you had to go into the account settings. Yeah.
Yes.
Yeah. Oh, that's good. That's good. Now we're up to 55. Okay, we'll start in when my clock says 5 minutes after in a few seconds. And everybody, please mute yourself when you enter. Okay, it's my pleasure to begin the next session. And the first speaker is Alina Czajka from Warsaw. Would you please begin?
Yeah. Okay, so thank you very much. So first, let me thank the organizers for the invitation. I'm very glad to have opportunity to present these results. And I will be talking about physical characteristics of glasma at very early times. And this is work done with Margaret Carrington and Stan Rubczynski, and it's based on our recent papers. So, and here is the outline of the talk. So after a short introduction and motivation, I will present a theory side and then like results. So I think that I will, in the theory side, I will just focus on like main theoretical tools which are needed to understand early time dynamics. And I think I will just only like sketch these main ideas. And just to say that this is quite well constituted background, and we only, when we were working on this, we just added some important contributions, but at technical level. So I won't be rather talking about this, but it's important to know that it helped to provide like more consistent approach to study this methodology. And then it leads to results which are also quite interesting. So yeah, so I will be talking about early time dynamics in this specific, like in MV model. MV model as a description of nuclei before the collision, then strongly interacting matter after the collision. So this is glasma expansion, and in very specific, studied in a very specific way by doing expansion in the proper time, which is quite unusual for early time dynamics. And then, of course, I will show correlators, which are based very useful, needed tool to do that. And then I will present results which we got, which is energy momentum tensor, pressure, anisotropy, azimuthal flow, and angular momentum of glasma. And then I summarize and conclude. So to introduce you to my studies and to show you a motivation, I think that it's fair to say that one of the biggest challenges in heavy ion physics is to understand what happens when we go from like early stage dynamics to hydrodynamics. And in studying like different systems. And I mean hydrodynamics in this case is traditional hydrodynamics, where it's understood as macroscopic effective theory based on conservation laws, which is quite a universal description of nature around us. And it is usually assumed that the system must be close to equilibrium. And it's just like very natural to ask what happens when we go from early time dynamics to hydrodynamics, when we imagine that at this highest energies, we produce a system which is described by microscopic theory of non-abelian gauge fields, and they are highly anisotropic and far from equilibrium. So it seems that there are two possible strategies, and the first one is that we see that this unreasonable effectiveness of hydrodynamics. So when we push hydrodynamics to the limits, where usually it's not expected to work or to be efficient, then we see that very interesting results, and then we see how sensitive it is to, or actually how insensitive it can be to different initial conditions. We see this attractor behavior that connects initial stage to this later time stage. And of course, by studying different theories, we can also get interesting universal, interesting results about its universality. But on the other hand, at the same time, we should just work out on initial stage of QGP evolution. Like there are like many things to do that, because basically there are no experimental direct. There's no direct experimental insight in initial stage. So it's important to find to constrain a theory about it to get more insightful knowledge about it. And of course, it boils down to like constrain numerical uncertainties, to include appropriate sources of fluctuations, and extend existing theoretical models, which is like important because it seems that at the beginning there are many approximations that are used. So we need to relax them in the era of measurement precisions and theory precision, and of course find new analytical tools. And then we are trying, by looking from both sides, we are trying to answer how many unique features of fluid dynamics we can find in the initial state made by gluons and quarks, and then to what extent QCD mimics hydrodynamic behavior. But of course, as we do usually in science and in life, caution is really, really required. And so in this talk, I'm going to focus on analytical approach to the initial state, which is purely classical. So this approach is quite, it has some good points, which that, for example, allows for control over different approximations and sources of errors. And it can be systematically extended, but on the other hand, we don't include like all possible fluctuations, or like some fluctuations which are included in different approaches. Like, for example, we don't include quantum fluctuations and these geometrical fluctuations of positions of nucleons or within nuclei. So in this way, it is still like less detailed when compared to other models, especially to IP glasma. And it cannot, at this moment, it cannot compete with that, but I think it can still provide some useful insight. And actually, this is at the same time, by providing results, we test this method just to show how applicable it is and how much, reliable the results, how reliable the method is in this context. Okay, so we want to study early time dynamics, so we need to know what is the theory, how nuclei can be described before the collision, and a well-constituted theory at highest energies to describe a nucleus before the collision is color glass condensate, which is given in terms of QCD quanta. And the special realization of CGC is MV model. And I will talk about this like simplest version, let's say, just in terms of general ideas. So then we just imagine a nucleus as a collection of partons, and there are like large X partons, like large like momentum partons, which are valence quarks, and they carry they are sources of colors, and they are represented by the color density rho, which is important for next pages. And so these color charges are sources of like small X partons. These are mostly gluons, and because of large occupation numbers of gluons, like soft gluons, they can be effectively represented by soft gluon field, which we call beta. And a color glass condensate is a useful theory. So in the sense it has this like saturation scale included. So we study this system in the saturation regime controlled by the saturation scale. And in the simple MV model, the separation scale is fixed. The separation scale between small x and large x partons is fixed. So, but also instead of gauge potentials, we can also describe a nucleus in terms of chromoelectric and chromomagnetic fields. And then we see just that longitudinal components of these fields vanish, they're basically zero, and only transverse components of these fields define the nucleus. And so this, just to give you a very simple summary of in terms of equations, so we see that the script, like at high energies, description of longitudinal physics separates from the transverse physics within the area of the transverse area of the nuclei. So it's useful to use light cone coordinates, and then write and then of course solve classical Yang-Mills equations, which are written here, where the color sources are given by for current, given by the rho, and the gluon fields are described by the strength tensor, and the potential field is there. And because the physics like along the beam and along within the transverse plane separates, so this model has quite like simple solution. And so the solution is this beta. So beta, like one of the components zero, that taking into account also gauge conditions, and the other, the beta I, is given by Wilson line, which includes the information about the color source. Interaction of the color source within the target. So having this in mind, we just now collide nuclei, and what we want to see what happens after the collision. So after the collision, glasma fields develop And what this means, it means basically that valence quarks, which are the color sources, they fly away from the interaction region, and the interaction region is like far from equilibrium system made mostly of gluon fields. And again, gluon fields, of course, are obtained as solutions to classical Young-Mills equations. And it's important to know that like, the valence quarks escape, but quarks can be still produced, but mostly by including quantum corrections, which appear next to the link order. And also it's important to know that there are many more approaches to study initial dynamics, and they are mostly based on numerical simulations, like geometrical, numerical, like Monte Carlo methods, or numerically solving the Young-Mills equations. And in this talk, I'm focusing on analytical approach, which is based on the fact that glasma fields, like the temporal evolution of glasma is obtained in the proper time expansion. So the glasma fields, so if we look again at equations, then we see that the gauge, that there exists an ansatz for the gauge potential in the forward light cone region. And the gauge potential is basically given by two glasma fields, which are like proper time dependent and are boost independent. And these equations again evolve according to sourceless Young-Mills, evolve according to sourceless Young-Mills equations, as you see. And we know that general solutions to these equations are not known, but we can find some methods to solve them. And it's important to notice that there is no like current dependence, like explicit current dependence here, as the sources are zero here, but the current dependence enters to these equations through boundary conditions. And boundary conditions connect different light cone sectors, or like both nuclear, like different light cone sectors through at the tau equals to 0, and they are given here. So at the beginning, glasma fields are just given by the pre-collision potentials, or in terms of chromodynamic fields, we can say that at the beginning, only longitudinal electric and magnetic fields develop in glasma, and transverse components develop later. So, and here is the method. This is expansion in the proper time, which is the time evolution of a glasma, the method to study, one of the methods to study temporal evolution of glasma. And this method was proposed like a few years ago. It was developed actually for many years. And in these two papers, especially, and the basic assumption is that we know from looking from different sides at initial stage that glasma is a short-lived phase, and equilibrium is reached quite early. So proper time of the system is of glasma is small, and it can be used as an expansion parameter. So in these two papers, it is proposed to expand glasma fields in a proper time, as you see here. And the same works for like strength tensor or like directly chromodynamic fields. And then we have still a system of coupled Young-Mills equations, and we can solve it recursively to any order in tau. And they expanded these fields, and they shown solutions to order 4. We extended it, and then zero order coefficients are identified with boundary conditions. So solutions for time evolution of glasma are given in terms of pre-collision potentials. And you can see that the like proper time is dimensionful, so effectively the parameter, the expansion parameter is just tau qs, like saturation scale, which is like 2GV in our case. And so we actually know how to study what is glasma. So, but let me for a moment go back to one nucleus, because we need like more insight how to describe one nucleus to get any information about glasma. So we know that color charge distributions are not known, and we need to somehow average over color sources. So we assume that just like Gaussian distribution of color sources within both nuclei, and it is given. And this is the ansatz, and it is like basic equation of MV model, where lambda is just where lambda volume density of sources gives charge density mu. And we also assume that potentials of different nuclei are uncorrelated. So then we can just find from the correlator of color sources, we can just obtain a correlator of gauge potentials, and it was derived also many years ago. And it is important to know that it is basic building block of energy momentum tensor and of all results later. This two-point correlator. But there are some important things to say about this correlator. So because if you see stress energy tensor is just like a combination of components of field of strength tensor, and we can realize that there are correlators of higher order. So in this case, we just use Wick's theorem to provide to write the like higher order, higher number of correlators in terms of two-point correlators. And we also
excuse me, Alina.
Yeah.
5 minutes, please.
Okay, I should speed up. Yeah, so we also assume that correlators of odd numbers of gauge fields vanish. And we also studied like two cases of energy momentum tensor where charge density is uniform and it's related to saturation scale, or it is given by Wood-Saxon distribution. And then it should be also mentioned that there are like infrared and ultraviolet regulators needed to find any results in these regimes. And the basic ingredients for our case for stress energy tensor is this in the correlator. It is actually 1-point correlator. So when the distance between 2 points goes to 0, so it is shown here. So this is actually to summarize that stress energy tensor is given by here, but we got the expression for it we got is quite complicated and long. There's no point to present it, but it just has like it is gauge invariant, divergenceless, traceless, and symmetric, and we like checked all these properties of it, and it has just this structure, and we obtained it up to tau to the 6th order. And then results. So first thing to check is, and to look at it, is energy density. So this is the energy density as a function of proper time for uniform mu. And we see that this allows to test the convergence of the proper time expansion. And we see that it can be reliable, the result can be reliable up to tau equals to 0.05, but we further test for other properties that this is really the case. And we see that we studied it for different geometries and Wood-Saxon parameters of Wood-Saxon distribution, and we see that this is basically a smooth function in time and space. Okay, then we studied also pressure. And so, and what we see that the transverse pressure, so on the left, we see transverse and longitudinal pressure as a function of tau, and we see actually the same for the energy density, that this method works reasonably well for times 0.055 Fermi, and we see that within this time the system approaches equilibrium. We see also that in the Wood-Saxon case, we see that the transverse pressure is quite sensitive to the geometry of the collision, and this sensitivity appears as a dependence on azimuthal angle and rapidity. And therefore, we observe some anisotropies. So this is the anisotropy of longitudinal and transverse pressure, and which is proposed as this formula is proposed to study this anisotropy. And so we see that by comparing different results for different impact parameters, we see that approach to equilibrium can be faster for central collisions. On the other hand, we also see that equilibrium can be achieved faster at space points in the reaction plane than rather than perpendicular to it. And also it is sensitive to rapidity, and it looks that equilibrium can be faster for larger rapidities. Okay, and because we have energy momentum tensor at hand, so we also can study like azimuthal flow given by Fourier coefficients according to this formula, and then we calculated V1, V2, and V3, and it seems that because so there are a few things that should be mentioned here. So we observe first that these Fourier coefficients are quite large, but V2 and V3 are of the same order as experimental values, while V1 is bigger than expected, like much bigger than expected. But it's also important to realize that this is on the initial stage. So the system undergoes subsequent hydrodynamic evolution. So it shouldn't be compared to experimental values, but we just observed some like flow coefficients they are. And there are some symmetries with respect to rapidity, because okay, we don't include all possible fluctuations, so it's just reflected by the size of them. And we see these are large, so we just calculated eccentricity, and we see the correlation between V2 and epsilon2, and usually it is treated as an indication of the onset of hydrodynamic behavior. So, and this correlation at this picture is shown as a red line. Okay, so this is quite interesting. And then we also computed angular momentum, but just let me first summarize that, like introduce what is the role of angular momentum. So it is this high it was realized that the angular momentum is large, produced in heavy ion collisions is large in non-central collisions, and it leads to like the like vorticity of the system. So we calculated angular momentum, and this is shown at the lower picture, at the bottom picture, and we see it is small, while for weak energies, it was computed 3 years ago, and it's clearly 10 to 5th larger than what we got, and it is very different. But we just say that the shape and positions of the peak are similar to previous results. And we just interpret this result as that most of the momentum is not transmitted to the glasma phase, because like valence quark carry the momentum and they just escape from the interaction region. And this is why glasma is not a rotating phase, and the polarization effect at highest energies for which our results are applicable, the polarization is not observed, and it is consistent. So this is summary and my conclusions, but I think I should stop since my time is over. So
Very good. Thank you very much.
yes, thank you very much.
Are there questions, please? Perhaps people are shy. If I could ask one question,
I have a hand up.
Oh, sorry. Go ahead.
You mentioned, you used several times in your presentation the word equilibration, for example, when the pressure anisotropy decreases. Yes. You said the system is moving towards equilibration. Is that, do you really have equilibration in the sense of entropy production and eventually settling down in a thermal equilibrium state, or do you rather mean isotropization, momentum isotropization?
I think that it's probably more like isotropization. We just see that it goes to that pressures, PL and PT go to like 1/3 as it is typical for isotropization. And
okay.
Equilibrium.
Is there another question?
You had one, right?
Yes, then I'll ask. You had that things tend to equilibrate at larger rapidity. Why is there a? You mentioned that a few slides back.
So.
Yes.
Yes. So we just see this, that for like zero rapidity, that the system needs more time so that anisotropy can be like isotropies, like balance. Just like this anisotropy should go to zero, right?
Yeah, I'm just, so where in your curves do you see that? I couldn't quite.
Okay, so the blue
out.
curve is the upper curve. It's for eta equals to 0, while, for example, the green curve and the red curve is for rapidity equals to 0.4.
Yeah, okay. Okay, so and again, it's, as Uli said, it's really more isotropization.
Yes, yes, okay, yes, in this sense, yes. So yeah, an isotropy is when it is 0, then we just mean isotropization.
Very good. Giorgio, do you want to ask one quick question? If it's quick, Giorgio, because we're over time.
Yeah, do we know whether this evolution in tau, basically perfect boost invariance in color glasses, stable against small perturbations?
Which perturbations?
Small perturbations. If you have a small perturbation that breaks boost invariance, does it grow or does it oscillate? Probably for you, it's not a problem because you have very early evolution. But
yes, yes. I think so. We just don't see any behavior like that.
Okay. Well, you don't.
Any oscillations? We don't see any oscillations. It's like the most stable.
Okay, thanks.
Okay, with that, thank you very much, Alina. If you could
okay,
stop
thank you,
sharing.
and sorry for taking too much time.
No, I'm a bad host. If you could stop sharing your screen, and I presume Renaud is here, and if you could share your screen.
All right, so can you hear me first?
We can hear you, we can't see your screen.
Right, so I cannot myself decide to share the screen. Say the host is disabling screen sharing.
Masood, could you?
Yes, Don.
Okay, can you try now?